physics students. Today I'm going to be going over a sample problem from Chapter 3, Sample Problem E, having to do with non-horizontally launched projectiles. Now, non-horizontally launched projectiles, I just want to review quickly, are projectiles. That means they're moving under the influence of only gravity, and they're moving in 2 dimensions, but they're not launched horizontally. That means they do have an initial velocity that is vertical and an initial velocity that's horizontal, as opposed to back in sample problem D where we had a horizontally launched projectile that had just an initial horizontal velocity but had no initial velocity in the x direction. Keep in mind that all projectiles follow this rule, that they have no acceleration in the x direction and they do have an acceleration in the y direction because they can be under the influence of only gravity. So let's dig into this question because it's kind of a hard one and kind of a long one, and we want to make sure we can get it all in one video. So what we've got is a zookeeper who finds an escaped monkey hanging from a light pole, and she aims a gun at the monkey, and what we see is that the monkey is 10 meters away horizontally and is 4 meters above the gun, 5 meters above the ground. And this dart comes out of that gun at 50 meters per second, but we're not really sure what angle it comes out of there. And then at the moment this zookeeper fires the dart, the monkey drops a banana. It's startled. So the banana falls under the influence of only gravity at the same time that a dart flies towards the monkey under the influence of only gravity. I want to take for a moment and just figure out what this angle is going to be. Can we figure out what the angle that they're shooting at here is? Well, as it turns out, we actually can, because we know this is 10 and we know this is 4. So, if you know that you've got yourself a right triangle and you know the sides of the triangle are 4 and 10, then you can find the angle that she's aiming at pretty easily. And the way you would do that is you're simply going to take the inverse tangent of 4 over 10. So what you want to do is use your calculator to take the inverse tangent, I'm doing it with my calculator right now, of 0.4. And when I do that, I find that the angle that she's actually aiming her gun at is 21.8 degrees. So that's a quick little way to figure out where she's aiming. She's aiming at 21.8 degrees. And then the next thing we can do is we can really kind of think about what would happen if this was a planet with no gravity. If you aimed a gun at a monkey hanging from a light pole on a planet with no gravity, that bullet is going to travel in a straight line and hit the monkey. But this isn't a planet with no gravity. This is a planet with gravity. So if you aim at the monkey, you're actually going to see that the bullet follows a projectile path. And that projectile path is a parabolic trajectory, which means aiming at the monkey will never hit it. You'd have to aim higher than the monkey. Anyone who's ever shot a gun or fired an arrow or something like this can tell you, you need to aim higher if you want to actually hit this monkey. But there's a really good chance you're going to hit the banana. In fact, this is a classic question where you'll actually, I can guarantee, you're going to hit the banana. And that's because the banana falls from the moment that you pull the trigger. And at that moment, the banana is falling under just the influence of gravity, and the dart is moving under just the influence of gravity. They're both being affected for the same amount of time by the same force and only that force. So they're going to be related. The catch here is just to keep in mind with projectile motion, and I did a demonstration of this in my class where I fired a marble in one direction and dropped a marble straight down at the same time, and those 2 marbles will hit the ground at the same time because objects moving straight down or in a curved path under influence of only gravity are still experiencing the same vertical component of their motion, regardless of their horizontal component. So what we really want to know is, can we prove mathematically that it'll hit the banana? And we can. Let me show you how we're going to do that. We're going to use the guess method. With the guess method, we can list the things that we know. And just like with any other projectile, we want to make an X column and a Y column. Things we know about the horizontal motion, things we know about the vertical motion. What we know about the horizontal motion is that it's going to travel 10 meters in the horizontal direction. we know that its initial velocity in the x direction is something that we can find using some right triangle trig. All right, so we'll do that in a moment. So we're going to know that. We can also, by the way, find its initial velocity in the y direction. We also know the acceleration. We know that whatever velocity it's fired at is not going to change because projectiles are only affected by gravity. So we know the acceleration in both directions. And we know however much time it takes for it to move in the x direction is the same as the amount of time it's going to take to move in the y direction. Because by definition, projectiles have to move in both these directions at the same time. So that will kind of help us out a little bit here. The hard part here is what is the unknown? And for us, the unknown is actually going to be what is delta y? Now you might be thinking, well, I know delta y. I know that it's got to travel 5 meters up in the air from the ground, or 4 meters from the end of the gun. But as it turns out, that will just tell us what the displacement is up to the monkey. But remember, we're not going to hit the monkey. We're actually going to hit the banana. Our question is what will the location of the dart be when it has traveled 10 meters in the x direction? If that's the same position, if it's at the same place as the banana, then by definition, if they're in the same place at the same time, then our dart has hit the banana. And that's what I want to prove that we actually are going to do here. When it comes to projectiles, pretty much there are two equations that are used for most projectile questions. One of them describes the x direction, the other one describes the y direction. So those are the two that we're going to be using today, these two equations. So these are our equations, and what we want to do is we want to solve initially for a couple of things. I want to figure out what the initial velocity in the x direction and the initial velocity in the y direction is going to be. So using a little right triangle trig, all right, I can see that the initial velocity in the x direction is going to be whatever the initial velocity of the projectile is, times the cosine of the angle. So that's going to be 50 times the cosine of 21.8. 50 I got from the question, and 21.8 I got from a little quick math. I can also tell you that the initial velocity in the y direction is going to be found in a similar way. So let's calculate those out. So I did a little quick calculator work, and I found that the initial velocity in the x direction is going to be 46.4 meters per second, and the initial velocity in the y direction is going to be 18.6 meters per second. Just did a little right triangle trig there. What it tells me is that this dart is moving way faster to the right than it is moving up, and that this velocity will not change because there's no acceleration. But this velocity will decrease to 0 when the dart is on the way up, and then eventually will increase from there once it reaches its apogee, because it's being accelerated downward constantly by gravity, even though it's moving upward. Now, that's really helpful, but what do I want to do next? Well, what I really want to know is, how much time is it going to take for this dart to travel 10 meters horizontally? Because if that's the same amount of time that it takes for the banana to drop 4 meters, or 5 meters, then it's possible that they could be in the same place at the same time. So let's see if we can figure out how much time it's going to take for the dart to travel 10 meters. To do that, we need to use this equation right here. What we want to do is we want to say, well, you know, the time that it's going to take is going to be its displacement divided by its initial velocity in the x direction. Its displacement is 10 meters, and I just figured out that its initial velocity is going to be about 46 meters per second. So what time is it going to take for it to get there? Well, my calculator tells me that that means it's going to take pretty much about 0.2 of a second for that dart to travel those 10 meters. Now, the next question is going to be, what height is that dart going to be at that time? And I can find that function. You put in a time, you put in the acceleration and gravity, and you put in initial velocity, and I'll tell you how high the dart is going to be at that moment. So let's calculate that out. So what I've done here is I've taken the variables that we know, and I've plugged them into that vertical equation. We said that the initial velocity in the y direction was 18.6 meters per second upward. And we said that the dart was going to be in the air for 0.22 seconds. We know that 1/2 is 0.5. Gravity is negative 9.81 meters per second squared. And again, the time it's going to be in the air is 0.22 seconds. So what we see is this first number that comes from this first part is 4.1 meters. What that number represents is exactly where the dart would be, the height the dart would be at if it was fired on a planet with no gravity. Remember that? We said, what if it was fired on a planet with no gravity? Well, after 0.22 seconds, boom, it'd be there. It would hit that monkey. However, this isn't a planet with no gravity. This is a planet with gravity. So it loses, this little back part here tells us that the effective gravity causes it to drop down by about a quarter of a meter. Gravity affects it during that time that it's in the air. So where will the dart be after it's traveled 10 meters? Well, it'll be 3.86 meters above, because this is a positive number, above the place where it was fired. In other words, it'll be right about here. It'll be at 10,4.86. And that's with respect to this as our 0 point. Okay? It'll be 4.86 meters above the ground and 10 meters to the right. Or 10,3.86 if you do it with respect to the edge of the rifle. Right. Now, that's great. We know where the dart will be after it's traveled 10 meters. But where will the banana be? Well, that's an important question. Remember, the banana is starting in the monkey's hand and is dropping. If we can prove that it's going to be right at that same point as the dart after 0.22 seconds, then we can safely convince everyone with math that the dart hits the banana. Well, the banana is in free fall, so it's falling in only the y direction. And really, we're using the exact same equation. We're using this equation, but it's dropped, which means this initial velocity is going to be 0. That pretty much X's out the whole rest of that front part. So this equation pretty much tells us the height, that the displacement of the banana when it's dropped. So we can see that it's going to be 0.5 times negative 9.8 times 0.22 squared. Because we want to know what height will it have dropped in those 0.22 seconds. Well, look, that's the same thing as this back part right here. I know the answer to this. It's going to have dropped 0.24 meters. That's how far it will have dropped during that time. Well, where did it start? It started at 10, 5. All right? It started at 10, 5 at time 0. Where will it be located after 0.22 seconds? Well, it will have dropped 0.24 meters, which means it'll be right there. What that tells us is, in the time that our dart moves this way, our banana moves this way, and our dart is going to hit our banana. This is a classic physics example of understanding that the vertical component of any non-horizontally launched projectile, actually any projectile, is just simply free fall. And this is a classic one. It shows up in college physics classes and first-year college physics classes every year. So it's a good one for you to see. But what I really want you to understand, the most important thing that we've learned here today, is that when dealing with projectiles, you must first break them into their x and y component. Second, recognize that time is the factor that connects the two equations. You're going to have one equation that describes what's happening in the x direction, another equation that happens in what happens in the y direction, and it's time that unites those equations. 9 times out of 10, your goal is going to be to solve that x equation for time and plug it into the y equation and figure out what position, x, y, your projectile is located at.